Good morning to all of you. It's a pleasure to be here. Thank you, the organizers, for giving me the chance to speak here. It's an educational session, so I will go very slowly through certain aspects of nonlinear low-dimensional dynamics. That's the first part of the introduction to dynamical systems. Afterwards, there's going to be a second one. Petra said in the introduction that this is an applied math presentation, that I will guide you through the applied math. One alternative title here would have been Introduction to Dynamical Systems, or How to Avoid Mathematics in the Understanding of Dynamics. So I'll try to be as unmathematical as possible, using a geometric approach that has been initially introduced by Henri Poincaré, but of course you will get some background about what is happening there. First of all, that's the abstract that you have in the handout. To start with, dynamical systems. How can we classify them, and where do we find them in nature? Here I did the following classification in terms of degrees of freedom. 1 degree of freedom, 2, 3 or many, until infinitely many, and the distinction between linear and nonlinear. This entire domain of applications of the linear world of dynamic systems is fully understood mathematically. There are no surprises whatsoever, and we can understand the dynamics of these systems 100%. Yeah. So that's, if you wish, it's boring on the one hand side, but we have it under full control. Yeah. It finds applications in decay or growth phenomena, oscillations, but not stable oscillations. We cannot stabilize an oscillation through a linear system. And then linear wave phenomena, I use examples here, heat and diffusion, etc. When we go to nonlinear phenomena, then we are in the domain of dynamic systems that are expressing a certain dynamics that can be stabilized. That's very important. You see here applications of biological oscillators, neurons, heart cells, the simplest model of a neuron we can find in 1D or 2D, so 1 or 2 dimensions. So I'm going to focus on this. When we go to 3D, we encounter the field of deterministic chaos, strange attractors, and here we are reaching the limits of our understanding. This is the frontiers of sciences. And studying brain systems, we are roughly here in this domain, right at the frontier of sciences. Another way to look at the world from a dynamics perspective is the following. Think of this as the amount of energy or information you're putting into a system. And then as this, certain structures that can emerge. And specifically, this would be a bifurcation diagram. We're going to speak about this in more detail. This would be the stationary states. If we're down here at 0, if you shut off a system from its environment, and do not provide any energy information and wait sufficiently long, the system will obey the laws of thermodynamics and basically decompose and follow its maximum entropy and fill a fixed volume with a gas, basically. Every structure starts decomposing. This is the field of thermodynamics. When we introduce more and more energy into the system, we go into the field of linear non-equilibrium theory. So this still thermodynamics where you make linear approximations, so deviations from the equilibrium. But then more and more energy into the system, you come into the domain of nonlinear dynamics, in particular synergetics, where multi-stable structures can emerge. We can have chaos with islands of stability. This is where life is. This is where biological systems operate. If we go even further, we approach the field of fully developed turbulence. Sometimes this is referred to as macroscopic chaos. This here is microscopic chaos. And here this is a deterministic chaos, which is low dimensional. Yeah? But live biological systems would be here. So, what I'm going to speak about, I will try to give you an introduction of the mathematical tools and concepts you encounter in nonlinear dynamical systems. This is referred to as one-dimensional flows and two-dimensional flows, about higher dimensional flows and the presence of noise. Andreas Daffertshofer will speak about afterwards. So we're going to focus on this, and we will try to understand structures as this and that. First of all, what is a dynamic system? In a dynamic system, you can define it by a triplet of the following entities. You need first a state space, which is spanned by the set of variables that describe your system unambiguously. If you have an n-dimensional system, you have an n-dimensional state space. An example is here. You have 3 variables, 1, 2, and 3. These are corresponding time series. And this is a corresponding state space, sometimes referred to also as phase space, this equivalent. And this time series that you see here is being plotted out as a trajectory in the state space. So temporal evolution of 3 variables, as you see here, is plotted in the state space as this is your initial point, and then as time evolves, it traces out a trajectory, a path in the state space. In addition, you need the notion of time, this is your time axis, and you need somehow a law, a map, a rule that tells you how the system shall evolve. So initial condition, state space, and then a map that defines the time evolution. And this map that defines evolution is exactly at the end of the day, our dynamic systems that we refer to as a differential equation, for instance. But there are other ways to deal with that. A few definitions. Phase space point, that's any point in the state space. Yeah? An attractor is a subset of phase space points towards which all trajectories move towards to. So it's attractive. A transient is exactly the segment between the initial point and the attractor. And a fixed point is a point in the phase space. Once you're on top of this point, then you're not moving anymore at all. So the rate of change there is 0. You will find at the end of your handout 3-4 pages a glossary, so with different definitions of individual terms. Let me try to give you an idea of these terms that I just used. Let me represent them here in terms of, this is a movie. So you have time series of 2 variables. We have dealing with a 2-dimensional system. So these 2 time series would have to be represented in a phase space that is spanned by 2 axes, this U and S here. And the time series that I just plotted here, they are fully equivalent to the trajectories that were plotted here. I'll go backwards. So this is the first time series that we saw, initial point, this is a transient, and then it goes very fast to this circular structure, and then it moves towards this red point. This red point would be a fixed point because there it stops. As you saw, all the trajectories in fact move to fixed points that are located on this circular structure, which is referred to as a manifold. Yeah? Manifold, a stable manifold in particular, is an attractive structure in this 2-dimensional state space. So you see these 2 representations are fully equivalent, and we can, in order to study the nature of a dynamic system, we have to study the geometry of these phase space trajectories. That's what I'd like to do with you now and in the following. Everything that all the concepts in principle about dynamic systems, not all, but many of them can be understood by the study of the simplest of all systems. These are one-dimensional systems. So, first of all, realizations of a dynamic system. This is a map that I refer to that carries the deterministic information about the behavior of a system. There are multiple ways to express this. The simplest and most straightforward way mathematically would be you write down the solution. X of t, x being your variable, equals something on the right-hand side. An oscillation would be sine omega t where sine is the sine function, omega is the oscillation frequency. That's trivial. But you can also represent a solution where an explicit solution in terms of another means that carries the identical information. Very often used are ordinary differential equations of this form. This is a time derivative equals a nonlinear function on the right-hand side, and k being a control parameter, and then a function on the right-hand side depends on the state variable itself. Yeah? But equivalent other ways are integral equations, integral differential equations. You can have equations with time delays, the latter being a mathematical structure that we encounter more and more in brain connectivity, simply because we have to take into account the delay of an action potential that travels from one side A to another side B. So the mathematical structure we will look at here in this course is this one here, ordinary differential equations, which are the most used representations of the lawful behavior of a dynamic systems. In one dimension, so x being the only state space variables, we can have only fixed points. When we go to 2 dimensions, we can have also oscillations. So having oscillations in this context means the dynamic system can describe oscillations. In other words, if you see oscillatory behavior in the system that you study, it must have at least 2 dimensions. It's not possible to have oscillations in 1D by definition. 1D meaning one state variable only. And 3 and higher dimensional flows, the way it works is when you go from 1D to 2D, you can have all the behaviors you have in 1D plus some additional behavior. And this is the way it works also when you go from 2D to 3D, same type of dynamic phenomena plus some additional phenomena, deterministic chaos, for instance. The tools I'd like to introduce you here to is what we already saw are time series. This is your measurements at the end of the day. Then you can represent these time series in phase flows. Yeah. So these are. I will define the notion flow in a second. But basically, it's the development of the trajectories in your phase space. Fully equivalent is potentials and gradient dynamics, as well as bifurcations. So these are the 4 levels of descriptions I'd like you to understand. And if this is all we accomplish here today in the morning, I'll be perfectly happy, because these concepts translate to higher dimensions also. So that's the reason why I'm going to spend some significant time on this. So one-dimensional flows. Why flows? What does the word flow mean? First of all, if we are in 1D, this here is our state space. We have only one vector, or one axis, and this is our state space variable x, and it can take different values here. Now, as we said, in 1D, we can have fixed points. This would be the following representation here, this dark circle and this light circle, or filled circle and empty circle. These are 2 fixed points. Now, if I take the dynamic system and put it here, it starts evolving towards this point, and if it does the same thing from the right-hand side towards this point, we talk about a stable fixed point. Yeah? So the direction of temporal behavior is indicated here through these triangles, or these arrows if you wish. They are indicating the flow. Yeah? So the temporal evolution of the dynamic system towards this stable fixed point. This here is an unstable fixed point. The dynamics evolves away from this particular point. This is all you can have, stable and unstable fixed points in one dimension. Please note the following, another notation. In the neighborhood of a fixed point, you're always slow. You're approaching the fixed point very slowly. Far away from it, you can be fast. You don't have to be fast, but you can be fast. This is indicated by these 3 triangles here. So the dynamics would be the following. I start here. Slow, slow, because this is in the neighborhood of the unstable fixed point. Slow, fast, slow. So the time course would be slow, fast, slow. in your mind, translate this into a time series. It would be kind of a sigmoidal curve. It starts slow. This is a time series that I'm drawing now with the laser pointer. Slow, fast, slow. Yeah? Okay, this structure here is captured by this equation. Yeah? It describes the flow. The flow on the right-hand side is determined by this equation by this nonlinear function f as a function of x and a control parameter k that somehow controls the system behavior. So now I can do the following. Since it's a function of x, I can plot this function f here vertically as a function of x. That's just an auxiliary way to understand the flow. Let me do this. Here I plotted the function f twice, once like this and another time like this. It's simply shifted upwards. Let's ignore the upward function for the moment and let's just look at this structure. That's the same one as we just discussed. See here. And so I'm plotting x dot equals f. So I'm plotting the function f over the horizontal axis x. So our nonlinear function looks like this. This is all. Now please note the following. We said this fixed point here is stable. What does that mean? It means if I look at f, the function f, to its right, it is negative. If I place my 0 here, it is negative. What does that mean? F is being negative, but f equals the rate of change. If the rate of change is negative, that means x moves towards smaller values. Okay? If x moves towards smaller values, it moves to the left, by definition, because increasing values of x go to the right. Same thing here. Here, f is positive. Yeah? Hence, the rate of change, which is x dot, temporal derivative, is positive. Hence, if I'm here, the system moves towards increasing values because the rate of change is positive. So I'm going to the right. This is the definition of a stable fixed point. The system, the nonlinear function is positive to its left, negative to its right, and by construction, same story here on the unstable fixed point, just the other way around. Another way to look at this is look at the slope of this function, the way it intersects the horizontal axis. It intersects it with a negative slope and here with a positive slope. There is more to it. Please look at it. Here, the flow, so the function f, is almost 0 on the fixed point, identical to 0 by definition, because a fixed point is defined as x dot equals 0. So by definition, here the same thing. It's just a slope that distinguishes these two, but here it has a big negative value. Big negative value means the rate of change is fast and very fast towards decreasing values. So it's negative. So you see the speed of the change here. If I start here, it's slow, fast, slow. That would be your corresponding time series. Yeah? This is, these 2 points here define a kind of a skeleton around which we have this type of dynamics. And this is all that can happen in the system. Now I can move this flow, this phase flow, or the nonlinear function, I can move it upwards, for instance, towards the point where we have no intersections. If we have no intersections with the horizontal curve, that means at no point there is a fixed point, which means the flow is always, in this case, positive, which means the system goes, look at it, here, a big value, it goes fast, slow, fast. That would be the behavior of this function here, and nothing else could be there. Yeah? This is the essence of this geometric approach. You can describe the interdynamics of the system as a flow on this one line. The same thing you can do in 2D, 3D, in as many dimensions as you wish. Visualization becomes an issue at some point. What we do is we study the structure of this flow to gain some insight about the underlying laws. Or in other words, the geometry, structure, and topology of these flows define the dynamics of the system and contain all the information. Now, we take this inside, and we start playing with it. Yeah? So, a few examples. This is what I mean by playing. Let's discuss a few examples. Let's gain more insights. Here, an explicit function now. X dot equals sine x. This is a sine function, 2 pi periodic. Our system lives in this one dimension here. It intersects with a positive slope, unstable fixed point, negative slope, a stable fixed point. In the neighborhood of a fixed point, always slow dynamics, slow, fast, slow. And then it repeats itself periodically because it's a periodic function. These are the corresponding time series. Let's go to this point here, pi. In the neighborhood of pi, stable fixed point. Let's go to the neighborhood of pi, and these are now the time series, a little to initial value, a little greater than pi. I go fast, and then I slow down and approach p, or pi, which corresponds roughly to this initial condition, fast and then slow. If I start here, I start slow, fast, slow. This is what you see here. I start slower, which means I almost, well, the slope here is smaller than this one, which means I start much slower. Then I speed up, and then it shallows out, which means I slow down. These are the different time series that you see. Make a mental note of this. What you typically, after a certain transient, this is your transient, what you find are your stationary points, your fixed points. But note that the transient carries much more information. You can also find unstable fixed points. These are the repellers. This is where you move away from, but slowly, yeah, due to the nature of a fixed point. So this is what you see here. Another example that we will discuss actually in detail is the following: x dot equals x squared. So this is a parabola. You see it intersects the horizontal curve in 2 points: negative slope, stable fixed point, positive slope, unstable fixed point. The corresponding time series are here. Unstable fixed point a little above. I go slow and I speed up, and I go to infinity in this case. And here, in the neighborhood of the stable fixed point, I move towards the stable fixed point. This is true for k smaller than 0. K just shifts this parabola up and down. Here I chose a negative value, hence we have intersections. If I move it upwards, k to greater values, what we see here is basically no intersection, and the corresponding time series is this one here. This is the part where it goes the slowest, and then it goes very, very fast. So I start roughly here, slow, 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 fast. This is the corresponding time series. Yeah. So you see, by changing this parameter k, I can manipulate the dynamics. I can generate and annihilate fixed points. I manipulate the fixed point skeleton. Generation and annihilation of fixed points is called a bifurcation. And there are only a set, in 1D, in one dimension, there are only 3 types of bifurcations that we can encounter. For k equals 0, the same system, rather than being above or below, this is exactly this point where this type of bifurcation occurs. I approach it from the left until I reach the fixed point here, and then I stop, because it's still a fixed point. But it's neither stable nor unstable. It's a critical point where the stable and the unstable fixed point have merged into one point. I approach it from the left, I leave it from the right. But there is no flow at all at this point. The corresponding time series look like this. Yeah. This point is marginally stable. The smallest perturbation or fluctuation, and you're across this barrier and you move to the right. Yeah? So the fixed point skeleton determines the interdynamics in a one-dimensional system. And once we start manipulating this fixed point skeleton, we talk about bifurcations. I'd like to discuss some of these bifurcations with you now. Actually, sorry. Before I do this, the mathematics that goes with the discussion of the stability of fixed points is called linear stability analysis. And what you do is basically you linearize around the fixed point. And the linearization basically means that if this is your nonlinear function f of x, at a chosen point, you fit it by means of a straight line. And you can, this is called a Taylor expansion. So f of x, you can Taylor expand every function. This is a value at the, this is a functional value at the value x0. Then you take the first derivative and look at its deviations. But you can also go to higher order terms, to the second order and the third order. This is a fit of y equals sine x that you see here. So this is a sine curve. And this dotted line would be a linear fit. So this is a slope. There you see most of the deviations are, the biggest error appears very close. But if you go to the next higher order, you see that corresponds to this function here. You already obtain a better fit of this. You can go even further. This is a fifth order fit here. Yeah? But if you want to fit the entire function, you have to go to order infinity. It's sufficient for linear stability just to look at this first term. So we can perform a linear stability analysis mathematically by calculating the slope at this point. And if it's negative, it's stable. If it's positive, it's unstable. Here are some extreme cases where you have to go to higher orders in order to understand this, because linear stability fails, because the first derivative is 0, which means it's neither negative nor positive. Yeah? But still you can discuss it geometrically. This here is a cubic function, for instance. You can approach it from the left and you approach it from the right, hence this is a stable fixed point. But there the linear stability analysis fails. But the geometric approach always works. So what we discussed are phase flows and time series. There is another way to describe the dynamics of a one-dimensional system in a manner that always works, using potentials. That's quite intuitive, but it can be also mathematized if you wish. So here you see let's look at the time series. We have all dynamics evolves towards the two stable fixed points. So that's like being in a potential landscape where a ball rolls down in a potential landscape and stops at the minimum. This is represented here. Here you have the horizontal axis, x, and this is your potential landscape. I call it V. And the two fixed points towards you wish to move are these 2 points that correspond to the two fixed points here. So it's like when you're on top of the unstable fixed point, you have the choice between going to the left or to the right. This is exactly that is expressed here. And it basically corresponds to the notion of having a ball rolling down the hill in a potential field. Yeah? Can we express this mathematically? And the answer is yes. If this is our nonlinear dynamic system with our nonlinear dynamic function, whenever I'm able to write this nonlinear function on the right-hand side as a gradient of a potential function V, then the system is a potential, then the system has a potential and can display only this type of dynamics. This is a corresponding potential. In 1D, this is always the case. Yeah? So we have always potential dynamics. The expression potential dynamics means the system moves towards a fixed point or away from a fixed point. Yeah? In 2D, this is not always the case. So I told you in one dimension we have a limited number of bifurcations. The saddle node bifurcation, the Pitchfork bifurcation, and the transcritical bifurcation. In the handout, I summarized all 4. I will discuss this one in detail. And then I will have to move on because we have a limited time only. But you have the detailed discussion of the bifurcations in the handout. And I'm using exactly the same terminology as I will use here in the discussion of the saddle node bifurcation. Saddle node bifurcation is the most basic bifurcation we know. How does it work? I'm displaying here 9 figures. By now, you encountered the language of phase flow, time series, and potential. I'm discussing the saddle node bifurcation along its generic representation. It's also called a normal form. What is that? What it means is whenever your system displays a saddle node bifurcation, you can write your system in this particular form here, sufficiently close to the bifurcation value. More to this in a second. So, but that's good to know. I told you there are only 3 bifurcations in one-dimensional systems. Yeah, 3 or 4. Pitchfork is a sub and supercritical version. So if there are only 3 or 4 bifurcations that exist in 1D and you believe your dynamic system is one-dimensional, then whenever you have a qualitative change in behavior, which we call bifurcation, then you know how to write the system and you're able to make predictions about its behavior. So that's a very useful thing to know. So this here is a normal form of the saddle node bifurcation. We discussed it before. It's a parabola opened upwards and with a control parameter k. In the column, you have different values for the control parameter. K smaller 0, k greater 0, and k equals 0. At k equals 0, it's always a point where the change in the qualitative behavior occurs. This is the critical value of the control parameter, the bifurcation value. Yeah? So the bifurcation occurs in this column. And in the rows, same story, using the same language, the 3 different terminologies that we have developed here. Let's look at the flow. Let's look here on the right-hand side. This is how we started off. For k smaller than 0, the phase flow of this system has 2 fixed points, a stable fixed point and an unstable fixed point. And the dynamics evolves towards the fixed point and the stable fixed point and away from the unstable fixed point. Here you see the equivalent behavior in the time series, unstable fixed point, stable fixed point. Or the corresponding potential function of this system is the following. You have one minimum, this is a minimum, and you have a well, basically a threshold. Basically, if you're sitting here and you get a kick, then the system, if the kick is big enough, can cross the threshold and start moving away, doing something else. Please make a mental note of the following. The saddle node system is also, is basically the simplest system I can think of that describes threshold behavior. And for us neuroscientists, the neuron is a threshold system, an excitable system that shows sub or super threshold behavior. If the system crosses the threshold, it generates an action potential. This is the minimal model for this type of behavior. If we increase the control parameter to its critical value, what happens is this parabola is being moved upwards. And then so what happens is these 2 fixed points start moving towards each other, meet, annihilate, and disappear entirely for values beyond the critical value. And then the corresponding flow looks like this with a time series with a corresponding potential. This is a saddle node bifurcation. Yeah? Most generic type of all the bifurcations that we have here. One way to summarize all this type of behavior is in form of a bifurcation diagram. That's another means of visualizing the qualitative dynamics of systems like this. This here is a bifurcation diagram. The same 9 cartoons of the dynamics, flow, time series, potential, the 3 columns. They are being captured in this representation, and that's basically what I showed you earlier as my 2nd or 3rd slide when I spoke about life, nature, the system going through, I showed you a bifurcation diagram. Yeah. So this is a bifurcation diagram of a saddle node bifurcation. Control parameter k. For negative values, we know there is a stable and unstable fixed point. The value of the stable fixed point I plot here. So that's on the vertical axis, I have the value of the fixed point. So the solid branch captures the behavior of the stable fixed point, and the dashed branch the behavior of the unstable fixed point. And as you see, as I increase my control parameter k towards 0, the critical point, these two fixed points merge into each other, and to its right there is nothing. Yeah? So we have a qualitative change of the fixed point skeleton. This is called a bifurcation. In particular, in this case, a saddle node bifurcation. All interesting things happen at these bifurcation points, because when you go from here to here, you just have quantitative changes. There's not much, no emergence of patterns, no reorganization, just a quantitative change. In most cases, such quantitative changes you can even renormalize away. So that's boring. All the interesting points, all the interesting behaviors you encounter here at these points. This is the reason why we have to understand these bifurcations. Another bifurcation, very quickly, is in this case a supercritical Pitchfork bifurcation. Here it's mathematical form. What it is, it's unstable fixed point, stable fixed point, stable fixed point. And as you change your control parameter k, what happens is actually that these two fixed points, the stable fixed points, they approach the unstable fixed point in the middle, which rests where it is until they collide with it. So they approach it from the left and right, so there is a symmetry. And as they collide, the unstable fixed point in the middle changes its nature from unstable to stable. Very intuitive is the visualization by means of a potential function. So corresponding to this, you have two minima and one well, one threshold in between. And as you go through the bifurcation, you have only one minimum, minimum. So often this is being used in terms of decision making, yeah? When you have a choice between two equal solutions, you start setting up a bistable potential. Yeah? So this is the situation. The corresponding bifurcation diagram is the following. Just focus on this. A branch of stable fixed points, in the middle an unstable fixed point, and these two collide, and the nature of the unstable fixed point changes at the bifurcation point and becomes stable. The third type of a bifurcation is a subcritical Pitchfork bifurcation, where let's just mathematically it almost looks like a Pitchfork bifurcation, just one sign has changed. But what we are having here is let's look at this one, one stable minimum surrounded by two thresholds, and when you cross the threshold, you move away to infinity. Please understand, bifurcations are only locally valid. They describe a system only locally. Once you move away from this region that is described by the generic equation capturing the flow in its neighborhood, here you see the system goes to minus infinity. Where to? I don't know. In this case, if this is all the dynamics, it goes to minus infinity. But there may be other nonlinearities that don't play a role in this neighborhood, but if you go further away, they start becoming dominant. That's a possibility. So bifurcations are always local in phase space. Yeah? And the corresponding bifurcation diagram of this of the subcritical Pitchfork bifurcation. The last one is a transcritical bifurcation, which in this case corresponds to an exchange of stability, unstable fixed point, stable fixed point, and as you go across the bifurcation, now here at 0, this point was unstable, now here at 0, it is stable. So it's as if one point travels through the origin. This is a transcritical bifurcation, and it's bifurcation diagram. So there was a very rapid tour through all the bifurcations we know. Again, saddle node is the most important one. This one I discussed extensively and in detail. And for the others, you basically have to, once you understand the concept, you have it understood, then you have to remember the corresponding normal forms. One other aspect that is also interesting in this case is the concept of hysteresis. I'm showing you the bifurcation diagram of a dynamic system of this form here that can be also written as a potential. Yeah? And this is the corresponding bifurcation diagram: stable, fixed point branch, unstable, stable fixed point branch. It has almost the same form as a supercritical Pitchfork bifurcation, except I'm adding a constant value. So this is now my control parameter. Think of, you have dirt in your system. Yeah? What happened, or some element that breaks the symmetry. Yeah? So before it was a Pitchfork bifurcation, and now I'm varying this parameter here. Look what happens to the bifurcation diagram. It actually, the symmetric form I am jumping backwards, I had here. Now, a beautiful symmetry now breaks actually into two branches that are being split into two saddle node bifurcations. This here is a saddle node bifurcation. Look at this locally, because again, bifurcations are valid locally. Locally, this means you have the approach, unstable fixed point, stable fixed point. They annihilate, and above the critical value, there is nothing. This is the saddle node bifurcation. So if you add some symmetry breaking parameter into a Pitchfork bifurcation, you break the symmetry, and like this, you make out of a Pitchfork a saddle node bifurcation. And then you generate phenomena such as hysteresis. You go, hysteresis is the following. Imagine you start here. You're jumping at a certain value k from one branch to the other and backwards. And then here, when you go backwards, you're not jumping from here to here. You're actually going to another value, at another value of k on the other branch. Yeah? So this is one-dimensional flows. Can I have 5 minutes, Petra? Because this is very basic, so I wanted to... Yeah, because this is actually very basic, and I anticipated that I will speak for about 50 minutes for exactly this reason, because it's the introduction. Yeah. Thank you. Very coarse and quick overview of two-dimensional flows. In two-dimensional systems, what you can see in addition to the fixed points are oscillations. But everything, all the mathematics and all the concepts that we discussed are the same. Yeah? So I will show you now a few phase flows to give you an idea of what can happen. First, I'm showing you the phase flow of a system of this form. Yeah? So it has a nonlinearity and a second dimension, which is y dot equals minus y. In terms of flow, it looks the following. Y is here, x is here. Please note that all the dynamics is being attracted towards y equals 0. So towards this point, go away from it towards this point. Yeah? So we have an, oops, sorry. Unstable fixed point here, unstable fixed point here. Stable fixed point here, stable fixed point here, unstable fixed point here. So the flow goes like this. One important theorem, it's called Hartmann-Grobman theorem. In the neighborhood of a fixed point, like this one here, unstable fixed point, the behavior of the system shows the identical behavior as its linearization. This is the following. I linearize the system, which means around x and y equals 0, which means I throw out the nonlinearity, and then I plot the phase flow. Do you see that this is the identical flow as we have here? Yeah? Except the nonlinear elements we don't capture. But once you start linearizing around all your fixed points in the flow, yeah, you develop your fixed point skeleton, this time in 2D, and you can start composing your system, building up a flow topology. And you have understood everything in your system. In terms of, I'm showing you two more flows to illustrate what kind of behaviors we can observe. This here along two neurally relevant systems. One is a neural model for, so a very simplified model for neural functioning. It's called, of a single neuron, not neural functioning, called Fitz-Yugnagumo system, the mathematics you have here. And let's construct the flow out of this. Yeah? We need one additional concept, the concept of a nullcline. You take x dot equals 0 and y dot equals 0 and plot these lines in this particular space here. So this is x dot equals 0, the first equation, which means I can rewrite this as y equals nonlinear function. This is this function here. So along this point, along this line, everywhere the flow x dot equals 0. Along the other line, y dot equals 0. Along this line, everywhere the flow in the y direction is 0. By definition, the flow at this point, x dot equals 0, y dot equals 0, this is a fixed point. If we want to understand the nature of this fixed point, we have to do a linear stability analysis. We don't have the time to do this, but this would be what would be needed to be done. I will show you the result. But now, understanding, having the topology of the flow in this neighborhood, we know basically everything about the system. Here you have the nonlinear function, its intersection with the other nullcline. You see here we have a fixed point. These are the corresponding time series. This is a stimulus, this is the x variable, this is a y variable. I'm introducing a stimulus and we obtain a deviation, but the system goes back to the original stable fixed point. Now I'm introducing a bigger stimulus. And what's happening is the system gets actually across a threshold and then travels through the state space and returns back to its fixed point. This here I could call subthreshold activity. This here is superthreshold activity, or another word would be an action potential. And neural state space has a structure like this. A fixed point, stable, a threshold somewhere here where large amplitude excursions can be performed. Or if I move the nullcline, this green line, towards the middle, then I can actually generate oscillatory behavior. I'm changing the phase flow. Or I can change the nullclines in other fashions and obtain bistable behavior. Think of an up state and a down state. These are the two other behaviors I just showed you. So, I'm almost done, Petra. This is a very famous neuron model called Maurice-Lécart, yeah, based on conductance-based modeling. It's almost impossible to understand what is going on when you look at the mathematics here. If you go, though, into the phase flow and plot the nullclines, you see, obtain immediately an understanding. This is a nullcline. This is the other nullcline. And as, this is a stable fixed point, unstable fixed point, unstable fixed point. Unstable fixed point, stable fixed point, which means if I go across here, this is what I'm doing here. Please note that the system performs this type of behavior and goes to the stable fixed point. Apparently here is a separatrix, a threshold element. If I'm staying to left of it, I'll go back to it, back to the stable fixed point. These are the two types of behaviors you observe in the time series. Out of the nullclines, you can construct its behavior immediately, and now, if you move the black nullcline further downwards, you see which kind of bifurcation? Saddle node. It collides, and you obtain actually oscillatory behavior, as you see here. I'm going to stop at this point. This is just a few words on potential dynamics, but let me stop here. At the end, you will find some more literature on further reading and, as I promised, a glossary. Thank you very much.